Welcome to our lesson on fractals and logarithms. So first off, what is a fractal? Well, it is a never-ending pattern that has the property of self-similarity. What do I mean by that? Well, if you were to zoom in on a fractal, you would see the same thing as you had seen when you were at the zoomed out position. Like what you see here. Whoa, that's trippy, man. That's seriously trippy. All right, let's move on. So, next thing I'm going to look at is dimension. You have a very good idea of what a dimension is. You know that, as they say, a single point has 0 dimension. A line has 1 dimension. A square is a 2-dimensional object. A cube is 3-dimensional. And if you can envision it, really imagine it, a hypercube, also known as a tesseract, is the 4-dimensional version of a cube. Is it possible to have a dimension in between whole numbers? Because all those examples we saw just now were whole number values of dimensions. Well, to answer that question, let's look at what is called the Hausdorff dimension, named after German mathematician Felix Hausdorff. So, Mr. Felix Hausdorff, he looked at things a little differently. He looked at scaling and copying to produce dimension. What do I mean by that? I mean that if you have a line which we consider to be 1-dimensional, if you wanted to make a line that is twice as long, which would be the scale factor r, you would need to make 2 copies of that line and place them end to end to produce a line that was twice as long. Similarly, for a line 3 times as long, you need to make 3 copies. If you had a 2-dimensional square and you wanted to make one that was twice as long in both directions, you would need to make not 2 copies, but instead 4 copies and place them around each other to get a square that would have been twice as long in all directions. You would then need to make 9 copies to make one that was 3 times as long in all directions. What about a 3-dimensional cube? To make a cube that was twice as long in each direction, you would need not 2, not 4, but instead 8 cubes. 8 copies of that cube would make another cube twice as long in all directions. And similarly, if you wanted to make one that was 3 times as long in all directions, it would not be 3 or 9, but instead 27 of those cubes. How did he come to that idea? Well, he studied the situation and found a formula that applies. That formula is n is equal to r to the d power, where n is the number of copies, d is the dimension of the object, and r is the magnification factor. So to look at that formula and apply it to the situation, let's say we looked at the cube and we wanted to make one that was twice as long in all directions. Here, it's a 3-dimensional object. We wanted to make it twice as long in all directions, or in other words, the scale factor r is 2. So 2 to the 3rd power gives you that there are 8 copies that need to be made, or in other words, n, the number of copies, is equal to 8. If you were to pause here and look at it for some of the other examples, you'll see that it works every time. So using this formula, we are to find the dimension of the Sierpinski triangle. So here, this fractal is known as the Sierpinski triangle, which is made by starting off with an original triangle, joining the midpoints of all 3 sides, removing that middle triangle, and repeating those steps infinitely for all remaining triangles. So, what is the dimension of this particular fractal? Well, we know our formula is n equals r to the d. N is the number of copies, r is the scaling factor, and d is the dimension. So the number of copies, let's say we looked at this small Sierpinski triangle here. Due to the properties of fractals, it is the same thing as the big one. It is just scaled down. We can take this one here and scale it up to produce this bigger version of the Sierpinski triangle. How many of these small ones do we need? How many copies? Do we need 4? No, we only need 3. This one at the top, the one at the bottom left, the one at the bottom right. We do not need a fourth one because in the middle here, it's just empty space. What is the value of r, our scale factor? Well, here, this has a side length of, let's say, 1, and so it has become twice as long along this edge on the left, then twice as long on that edge on the right, and twice as long on the bottom. So r is 2. So n, our number of copies, is 3. R, our scale factor, is 2. The dimension is d. 3 is equal to 2 to the d power. What can be the value of d? Well, if we think about it, 2 to the first power is equal to 2. 2 to the second power is equal to 4. But 3 is in between 2 and 4. So the value of the dimension d has to be a number between 1 and 2. How do we find it exactly? By using logarithms. So if we take logs of both sides, we'll have that the log of 3 is equal to the log of 2 to the d power. Applying our laws of logarithms, if we have 2 to the d power, we then take that d and multiply it times the log of 2. d times the log of 2 is equal to the log of 3. So to find d, we take the log of 3 and divide it by the log of 2, which will give us that d is equal to 1.58, which is indeed a number between 1 and 2. So the Sierpinski triangle is not exactly a two-dimensional object, nor is it a one-dimensional object. Its dimension is fractional between 1 and 2 dimensions. So with that, our lesson ends here.